Hello guys, welcome to my channel. Today our problem is max sum of rectangle no larger than k. Given a non-empty 2D matrix and an integer k, find the max sum of a rectangle in the matrix such that its sum is no larger than k. So for this example, we are looking for a max sum of rectangle so that the sum is not larger than 2. In this case, we have this here, so the max sum is 2. Alright. When this is asking for no larger than k, we can first rephrase it a little bit. So we are actually looking for a sum that is smaller or equal to k, right? The largest smaller or equal to k. All right. First of all, let's simplify this problem a little bit. Let's start from 1D array. So if in a 1D array we are also looking for the next subarray sum that is largest smaller or equal to k. How do we do that? Well, every time if we are not coming up with a good approach, we can always start from a brute force idea. So here, the brute force idea for a 1D array could be, we first use a double for loop to generate out all possible subarrays and then sum each subarray. And out of all possibilities, we look for the maximum subarray sum. So for that, if n represents the length of the 1D array, so for that it's n to the third power, because so let me elaborate it a little bit. So step 1 is we generate out all subarrays. So this step is n squared. Step 2, for each subarray, we sum it up. So for this step, we also need n time complexity. So the total time complexity is n to the cube. This is a brute force idea. And based on the brute force idea, we know that for the second step, we are doing a repetitive work each time we generate out a subarray. And for that, we can actually use prefix sum to optimize it, right? After using prefix sum, the time complexity could be n squared now. And how can we optimize further? Further optimize. By looking at the time complexity, we reduce the time cost from n cubed to n squared. Which means if we want to optimize it further, the next algorithm must be n log n or on, right? So in this case, I still want to use prefix sum to for the optimization. So if our current prefix sum minus a previous prefix sum is less or equal to k, that means there is a subarray existing that is less or equal to k, right? So which means we are supposed to look for this previous prefix sum. If I convert this formula a little bit, previous prefix sum, it's gonna be k minus prefix sum, and then the previous prefix sum we are looking for has to be minus k, right? So basically we are looking for the x, the previous prefix sum that is the smallest, larger than or equal to prefix sum minus k. All right. All right. So that's how we are able to look for the subarray. Cool. So in this case, the time complexity would be n log n, because in this case we are using a tree set for the algorithm. Yeah. All right. So this is for the 1D. How about 2D then? So the difficult part for 2D is that we have to come up with an idea to convert our 2D matrix to 1D. And then the rest of the work is just the same as we just did for the 1D array. But how can we convert it to 1D array? Well, basically, we could, so the step 1 can be we generate out all consecutive row combinations and add them up. Then this is how we could convert 2D to 1D. Step 2 is same thing as step as 1D array, right? Okay. If we are generating out all consecutive row combination, in this case, if m represents the total row for the matrix and represents the total columns for the matrix, then the time complexity for generating out or the combinations is m times n for sure. And for step 2, is n log n. So the total complexity for this one is m minus n times n log n. Well, because in this case we are generating out all the combinations by row, but it does not have to be. It really depends on which, whether or not the length of the row is smaller, shorter than the length of the column, right? So if the length of the column is actually smaller, then it's preferred that we use consecutive column combinations instead. All right, let's get started. So right, and following the first step, we generating out all consecutive row combinations. So oops, here should be at. So as we generating out all combinations, we add them, and then we use a tree set to look for the maximum sum. So here the maximum sum is if max sum is equal to k, then we have reached the top. So we return directly. Otherwise, we If still equal to the minimum value, then negative infinity, then it's a -1 because we do not find any. Otherwise, we return max. All right. Tree sets. So for the tree sets, as we initialize it, we add 0 at first, and then prefix sum equal to 0. Whoops, I forgot to add in the Alright, here is where we are looking for the separate sum. We're looking for a ceiling. So tree set. So if the prefix sum, if there is a previous prefix sum existing, that means there is a separate sum that qualifies what we are looking for, right? And if there is a separate exactly equal to k, then we just return k directly. Otherwise, we update our current max. Right? So this is it. And then return current max. And void sum. Columns. Right. Right, I think that is it. So let me double check. So here, I'm generating all consecutive row combinations and starting from the first row. And then for each one, I add them up to a 1D array. I sum all of them here. And I use a tree set to look for the maximum sum using a helper function. Right. if it exists, we update the current max here. Right, let me run the code. Yeah, there is a syntax error. Oh, hash stats. Cool. Wait. I think I forgot one thing because we are accumulating the prefix sum, but at the same time we have to update add in the new prefix sum into our tree set, right? Right. Cool. Thank you for watching. See you guys next time.